Again, we have a function where we're trying to find out where is it increasing, where is it decreasing, and determine any local or relative extrema of the function. To do this, again, the first step is to look at the derivative. The derivative of this function would be 3 times 2/3 x to the negative 1/3 minus 2. Well, let's go ahead and simplify that. Looks like the 3's are going to simplify to me. And it looks like we have a 2 over the cube root of x minus 2. And this is my derivative function. The first thing I want to do is think about when is this equal to 0 and when is this undefined. In this case, we are going to have a point where it's undefined because we do have a fraction. Remember, the denominator of a fraction cannot equal 0. So we know this will be undefined anytime the denominator, which is the cube root of x, is equal to 0. We'll solve both of these equations now. Solving the first equation, first thing I do is I add 2 to both sides. Then I'd have 2 over the cube root of x equals 2. I need to get rid of the cube root of x, so I multiply both sides by the cube root of x. That would leave me with 2 equals 2 times the cube root of x. I divide both sides of the equation by 2, which would give me 1 equals the cube root of x. I need to get rid of the cube root, so I cube both sides, and I end up with x equals 1, which is in the domain of the original function, so it is a critical value. At the second equation, when is the denominator equal to 0? That's when the cube root of x equals 0. Simply cube both sides. That gives me x equals 0, which is in the domain of the original function, so I know that 0 is also a critical value. So now I'm going to look at my real number line, plotting the points 0 and 1. I'm going to consider the derivative at those points. At 0, it was undefined, and at 1, it was 0. I consider the intervals between those points. Negative infinity to 0 is the first one, 0 to 1 is the second, 1 to infinity is the third. I need to create a sign chart and test a point in each one of those intervals. Again, I'm plugging it into the derivative here to find whether the function is increasing or decreasing. That's 2 over the cube root of x minus 2. A number in the first interval that I want to pick. How about I'll pick the number, I don't know, negative 10. That's between negative infinity and 0. A number between 0 and 1. I don't know, why don't I pick something like 1/8, a number that's easy to take the cube root of. And a number between 1 and infinity, I'll pick the number, how about 8. I'm going to go ahead and I plug these into my calculator, and I'll see what I get for each one of them, whether they're positive or negative. Plugging negative 10 into this function, for my first function, I ended up with a negative, or for negative 10, I ended up with negative. So that means everything on that interval must be negative. On the second interval, 1/8 tested positive, so that means everything on that interval must be positive. When I plugged in an 8, I got a negative, so everything on that interval must be negative. So again, my function then, if I'm looking at what happens to my function on each of those intervals, because the derivative is negative, my function is decreasing. Derivative positive means my function's increasing. Derivative negative means decreasing. So looking for the points in total where it is increasing, I'm going to be looking at the interval 0 to 1. Looking for when is it decreasing, I'm going to be looking at the intervals negative infinity to 0 and 1 to infinity. So that leaves when do I have maximums and minimums? Again, local or relative, same word there. Well, anytime it changes from decreasing to increasing, I have a minimum, and anytime it changes from increasing to decreasing, I have a maximum, as long as it's in the domain of the function. Both of these points were critical values. They were in the domain of the function. So I have the x values of each of these. The x value of the maximum is 1, and the x value of the minimum was 0. I need to find those y values. Again, the only way to find the y values is to plug them back into the original function, which I will do now. So I'm taking my x values, and I want to plug them into the original function, which was 3x to the 2/3 minus 2x. If I plug in the number, well, I have to plug in 0 first. If I plug in 0, I'd have 3 times 0 to the 2/3 minus 2 times 0. Using my calculator, I get 0. And then I need to plug in the x value of 1. 3 times 1 to the 2/3 minus 2 times 1 is the number 1. So I know at the point 0, 0, I have a minimum. And I know at the point 1, 1, I have a maximum. Finishing off my answers to the problem. So what we just did was intervals of increasing, decreasing, and what was called local or relative extrema. Relative extrema mean you have a highest or lowest point in some interval. This is different from absolute extrema. Absolute extrema means it is the absolute highest point. For instance, look at this graph right here. I can see that I would have two different relative maximum, this point right here and this point right here, but one of the maximums is higher than the other. The one that is the highest of all relative maximum is called the absolute maximum. Likewise, looking at this graph, I actually have two relative minimums, two lowest points in the graph, but the absolute minimum would be the point that's lowest over the entire specified interval or domain of the graph. So what we're looking at now is how do we find the absolute minimum and the absolute maximum of a function on a given interval. This is a very, very different process than increasing, decreasing, and relative extrema. Again, I cannot emphasize that enough. Finding absolute extrema is a very, very different process than finding relative extrema. The first thing we want to notice is where can absolute extrema occur. Absolute extrema have to occur at an endpoint of an interval or at a relative maximum. Absolute minimum, again, must occur at endpoints or at relative extrema. So if it is an absolute extrema, it is either an endpoint or it is at a relative maximum or minimum. So, the extreme value theorem first states, as long as we're a continuous function, no hops, skips, jumps, or anything like that, and we're on a closed interval, then you have to have a minimum value and a maximum value. So the question is, how do we find it? The extreme value theorem just says it's there. How do we find it? So here's our guidelines or our steps for doing it. The first thing we need to do is find those critical numbers, which would be the points where the derivatives equal to 0 or undefined. And then we're going to look at the endpoints and the critical numbers because we know any maximum or minimum must occur at the endpoints or at the critical numbers. Rather than finding the derivative of the function where it's increasing, decreasing, and plugging in the numbers to the derivative of the function, we actually, for absolute extrema, plug these numbers into the original function. So find the critical numbers where the derivatives equal to 0 or undefined. Then you're going to plug in any of the critical numbers and the endpoints into the original function. Whichever one has the highest y value is the absolute maximum. Whichever one has the lowest y value is the absolute minimum. Again, find the critical numbers, go to the original function, plug in endpoints and relative extrema to the original function, not the derivative. The highest value is your absolute max, the lowest value is your absolute min.